Welcome everyone to the second lecture in quantitative risk management. And as you can see from the outline, after having talked a little bit about differential and descriptive statistics, inferential and descriptive statistics, we've now moved on to statistical distributions and processes. What is the background here? In most applications in quantitative risk management, we have to deal with the statistical modeling of profit and loss distributions or just loss distributions. And for this, obviously, we need to use statistical distributions and certain processes, stochastic processes, and we'll discuss the most frequently used distributions and processes here before then going on and using these distributions in applications and in the modeling of financial losses. We'll start with very simple probability distributions on the real line and then move on to multivariate distributions before talking a little bit about copulas. Copulas being basically the mathematical instruments with which we can glue together univariate probability distributions and come up with multivariate distributions. And then in the time domain, we'll be looking at stochastic processes. So these are sets of distributions, it's probably best to talk about this later on when we see the definitions, because otherwise, if you haven't had the luck to talk about stochastic processes before, and if you haven't heard about stochastic processes before, this is probably a little bit difficult for you without the proper mathematical definitions. So we'll start with very simple probability distributions that we'll be using every now and then throughout this lecture. So we'll start with some right-skewed probability distributions, for example, the log-normal distribution. And in our practical applications, the right-skewed, that is the right-tailed random variables, are often used to model risk and claim size, especially in insurance mathematics. And one distribution that is frequently used is the beta distribution. It has two parameters, alpha and beta. It is defined on the unit interval from 0 to 1, and it depends on those two non-negative parameters alpha and beta. The probability density function, it's a continuous one, is given by this expression here. So it's defined on the unit interval, as I said, and it is 0 otherwise. And with beta, alpha and beta being the beta function, you can look that up on the internet or in textbooks. And we need this for scaling the probability density function so that it is actually probability density. And if, for example, a random variable x is distributed according to a beta distribution with alpha and beta as parameters, we have alpha, the parameter alpha, divided by alpha plus beta as its expected value. And the variance of x is also given as a function in alpha and beta. So that's the beta function. On the next slide, you can see three different probability density functions for three different beta distributions with different alpha and beta parameters. And as you can see, especially with the black one, this is a right-tailed one. So the tail goes off extremely long here on the right-hand side. And obviously, it is only defined on the unit interval between 0 and 1. So that's the probability density function. Sometimes we also use the so-called Burr or Burr type 12 distribution. This is most commonly used to model household income, especially in economics. And the PDF now is given by this expression. You don't need to remember all these definitions, but you need to know that we have three parameters, C, K, and lambda. And it is a distribution that is defined on the positive real line, on the non-negative real line, which makes sense if you want to model household income. And this is what the Burr distribution looks like for three different sets of parameters. could make sense to model a given risk factor using this type. Next one is the inverse Gaussian distribution, or the so-called wall distribution. It is denominated by inverse n of lambda and mu. It's a 2-parameter family. It is also continuous for positive real numbers. It looks pretty much like a normal distribution, but it is slightly different from the standard normal distribution. We have the expected value being mu and the variance being the third power of mu divided by lambda. And if you invert it, if you take x and you invert it with respect to multiplication, you can see that the expected value of 1 over x is 1 over mu plus 1 over lambda, and basically the same one with the variance. And you get these distributions here, the inverse Gaussian distribution. It is quite interesting. Just me, I was just seeing the question here. In big blue button. Is the slide on BBB still at the outline slide? No, it has actually moved on to slide 62 now. Okay. And you can see that the inverse Gaussian distribution is very often used to model credit risk losses. You start out at 0. If you only concentrate on the losses that come about from credit risk, from, for example, loans you've given to borrowers. You're not interested in the profits at this point here. So the best thing you can actually achieve is that you have no loss at all. And the bulk of financial losses will probably be somewhere very close to 0. So it's very high here. It then goes to the median and the mean, probably around here, and then it goes off to the right hand side, and you have a very, very small probability of a very, very high loss. Now this would be somewhere here. So the probability density function is very low here, so there's a small probability, but it could be a very high loss here on the x-axis. So that's an inverse Gaussian distribution. Next, we have the so-called log normal distribution, which comes about by taking the logarithm of a normally distributed random variable. So it's the continuous probability distribution of an RV whose logarithm is normally distributed. So if x is normally distributed, then if you insert x in the exponential function, then y, being the exponential function of x, is log normally distributed, with the expected value of y being exponential function of mu plus sigma squared divided by 2, and the variance also being a function in the exponential function. And the PDF for the log normal distribution is given by this expression here. And the log normal distribution is frequently seen in option models. We'll later on see when we talk about stochastic processes that with certain stochastic processes, you are actually assuming a log normal distribution of prices for an underlying, which will result in a normal distribution of returns. So you have a normal distribution of log returns and a log normal distribution of asset prices. And this is frequently seen in the Black-Scholes model. Again, on this slide here, 64, you can see the examples for the log normal distribution. And this is also a distribution that is frequently used for log return or for returns or for prices, but also for credit risks, for losses that result from credit investments. Next is the Pareto and the Weibull distribution. Now the Pareto distribution, as the first one, depends on 2 parameters, alpha and d. And it has frequently been used to describe the distribution of wealth in a society, but it's also often applied to the modeling of losses which exceed a certain threshold d. And the PDF is given by alpha d taken to the alpha power divided by x to the alpha plus 1 power for x that are larger than d. And the expected value exists for alpha as a parameter being larger than 1, and the variance exists for alpha larger than 2. And the Weibull distribution, which is closely related, has a rather similar PDF, and it is used in a similar context. Now, extreme value theory, which we'll be talking about at the very end of this lecture, and additional extreme value distributions, they are covered in the last lecture. It is sufficient to say at this point that you can generalize the Pareto distribution, and in extreme value theory, where, for example, you are looking, if this is your distribution, you are looking only at the values at this leg or in this tail of the distribution, that for some reason, and we'll discuss this in detail, the points at the tails of, let's say, a regular distribution, the observations in these tails, they follow something similar to a Pareto and a Weibull distribution. And this is what extreme value theory is about, and we'll cover this in the very end of this lecture. So these are 3 examples for the probability density function of a Pareto distribution. They start out all here, and then they have a jump, and they go off to the right. Okay, so these are some additional distributions. We know the normal distribution, we know what a t-distribution is, but we also now know the Weibull, Pareto, Burr, and beta distribution, which we'll be using from time to time. Then let's turn to multivariate distribution. Now, you probably know that we have univariate distributions and multivariate distributions. If you have one random variable, it is univariately distributed, for example, according to a student t, according to a Gaussian distribution. If you have 2 random variables or more, x1, x2, up until xp, you can also look at the multivariate distribution of the random vector. The random vector would be x, and it is simply the combination of x1, x2, and so on. And then you can imagine that you have, for example, 2 dice that you roll, and you have a uniform distribution with the first one and a uniform distribution with the second one. And if those 2 are fair, you would expect that they are randomly and independently distributed. So you have stochastic independence between those 2, x1 and x2. But it could also be that the result from the first one affects the result of the second one. And this is where we have stochastic dependence. And stochastic dependence is only captured in the multivariate distribution of x1, x2, and so on. So we'll start with the random vector following a so-called multivariate or normal distribution, the most basic form of a random variable in multivariate dimension. Its distribution is uniquely determined by a vector of expected values, mu1 to mu p, and the covariance matrix. And more generally, you could also exchange this. It's very simple to see that you only need, say, mu1, mu2, sigma 1, sigma 2. So you need the parameters of the, in 2 dimensions, the parameters of the 2 normal distributions. And then what you need else is the covariance between 1 and 2, or alternatively the correlation between the 2. And sigma 1, sigma 2, and the covariance, those are also included in the covariance matrix, because the covariance between 1 and 1 is nothing but the variance. So this is all you need for the multivariate normal distribution. You need the expected values, mu1, mu2, and so on, and the covariance matrix, which are basically the standard volatilities or the variances plus the covariances. Then the probability density function at x is given by this expression here. It looks like a normal distribution, makes sense. And you need to insert not the volatility, but the covariance matrix here. And you need to insert the vector of expected values. And then it's quite clear, mu j is the expected value of the jth random variable. Sigma jj is the variance of the jth random variable, but sigma jk is the covariance between those two variables j and k. That's how these are the parameters you need. And obviously mu and sigma jj, those are the parameters that drive the univariate marginal distributions. And sigma jk, these are the parameters that drive the dependent structure between those random variables. This is the PDF of a two-dimensional multivariate random variable normal distribution. You have x and j, and on the z-axis you have the probability density. You probably know that the multivariate normal distribution is also called a Gaussian bell distribution. This is why it's called a bell, because it looks like a bell. It's very symmetric. It's symmetric, not very symmetric, it's symmetric. And yeah, that is a two-dimensional multivariate normal distribution. Now, all marginal distributions are again normally distributed. That is, xj is distributed according to a normal distribution with mu j and sigma jj, the variance, as the two parameters. And if you take any division, any subset of x, say for example you have x1, x2, x3 and x4, and if you split it up into x1, x2 and x3, x4, without loss of generality, we can assume that, for example, x1 is x1 up until xk, and x2, the vector is xk plus 1 up until xp. Then it is again normally distributed. You can simply divide this vector up into two sets of vectors, and again what you get is a normally distributed random variable, or you get normally distributed random vectors. Okay. Now, if x follows a multivariate normal distribution, we also know that every linear combination of x also follows a multivariate normal distribution. That is, for A being a P times Q matrix with full column rank and B a Q times 1 vector, we get A times x plus B is again normally distributed in a multivariate normal distribution with a slightly different expected value vector and obviously a slightly different covariance matrix, which result from this linear operation, from this linear function ax plus b, which simply means that if you have a random variable a random vector that is normally distributed and you insert it into a linear function, the resulting multivariate distribution will also be normal with slightly different parameters. And the multivariate normal distribution is often used to approximate the distribution of multidimensional metric random variables because of the how is it called in English? I'm sorry for that. Because of the central limit theorem, zentraler Grenzwertsatz, and we'll be talking a lot about the pros and cons of using the multivariate normal distribution in this lecture. On the pro side, you can show that if you have a large enough sample, it makes sense to use a multivariate normal distribution because in the end, because of the central limit theorem, it is easy to show that the stochastic behavior of any metric random variable will go to the normal distribution in limit. so it will converge to the normal distribution. However, the problem is, in many applications, especially in finance and in risk management, when we assume a normal distribution, we have certain problems associated with a normal distribution that make risk measurement quite tricky. Most importantly, what you can see is the normal distribution, even in one dimension, is one-dimensional, is symmetric, and it's not leptokurtic. So in many cases, you have a non-symmetric distribution with a slight bias to the left, which means that losses are more probable than under a normal distribution, and the tails are fatter than with a normal distribution. And these are two empirical stylized facts we need to account for when using statistical distributions for modeling losses, and this is where the normal distribution fails. So it is justified inter alia by the fact that when estimating multidimensional parameters, for example via maximum likelihood, the parameters are asymptotically normally distributed. And building on that, one can calculate confidence intervals or perform hypothesis testing. However, that is only in limits when n, the sample size, goes to infinity. And in many applications, that is not the case, and this result does not hold empirically. Okay, so that's the multivariate normal distribution. Then let's turn to the multinomial distribution, which is a generalization of the binomial distribution. And we can model, for example, the probability of counts for rolling a dice n times. And the multinomial distribution gives the probability of an arbitrary combination of numbers or successes for each of the 6 possible numbers of pairs. So more formally, if the possible outcomes are A1 up to AK, for example 1, 2, 3, 4, 5, 6, with probabilities Pj, and j being 1 to k of course, and if the number of trials is n, so we take a dice, we throw it n times, and we want to know the probability of rolling 3 sixes. Then it's x1 until x2, x3, and it's a multinomial distribution with n, and I'm pretty sure this has to be a small n, because we haven't defined a capital N by now. P1, Pk, those are the individual probabilities of rolling a 1 or 2 or 3. Could also be an example with A1 being male, A2 being female, and maybe A3 being diverse. So we could do the same with gender. Xj denoting the number of successes for outcome j. Then for x1 until xk, it follows that the probability of rolling x1 in the first try, x2 in the second try, and so on, is n factorial over x1 factorial times and xk factorial times the product of all those probabilities taken to the x1th power. That's the binomial probability, and from these probabilities we can build the multinomial distribution. Okay. There are huge numbers of different distributions you could also be using. If you are ever in doubt, go to the library, go to the literature, take up a statistical textbook on statistics and on statistical distributions, and I would assume for every purpose you can get your freak distribution that you've probably never heard of, but there are so many probability distributions around that should be well suited for your particular purpose. I've only presented to you the most basic ones. So we have one multinomial, we have the multivariate normal distribution, and all those different univariate ones. So let's turn to copulas, which are an instrument with which you can combine univariate distributions and come up with new multivariate distributions. So the starting point is that we've already seen several times that in past lectures on finance, on banking, in financial risk management, that we are concerned about portfolio risk and we want to measure portfolio risk. And portfolio risk includes not only the risk of looking at the marginal redistributions, but also modeling the dependence structure between those individual risks. And we'll talk about CCC, DCC gauge models. You might have heard about these in previous lectures on econometrics. And most of these models, they exclusively use linear correlations, just like in a normal distribution, to represent the dependence structure. However, as the term implies, linear correlations can only capture linear dependencies. So if we are interested in nonlinear dependencies, we need to model and describe the complete dependence structure, and that is what we are doing here by the use of copulas, which we'll introduce next. So what is a copula? A copula basically is a very special distribution function. It's actually a d-dimensional distribution function on the d-dimensional hypercube, unit hypercube, 0 to 1. What does it mean? In one dimension, it would be the unit line from 0 to 1. In 2 dimensions, it would be the unit rectangle. In 3 dimensions, it would be the unit cube. And in more than 3 dimensions, it would be the unit hypercube, the d-dimensional unit hypercube. And a distribution on the unit hypercube with the univariate, uniformly distributed marginal distributions on the interval 0 to 1, any distribution that fulfills this requirement is a copula. And we'll write a copula in this way, C of this vector u, and that is a function in the arguments u1, u2 up until ud, and each u1, u2, ud, etc. is taken. So let's say uj is element of the unit interval between 0 and 1. What a copula actually does is it takes the marginal probabilities and it combines those marginal probabilities, which should be between 0 and 1, and it recombines them into one new joint probability. So a copula, generally speaking, is nothing more than a special distribution function with uniformly distributed margins. However, it can also be interpreted as a function that takes d uniform random, marginal probabilities, and it combines those marginal probabilities into one joint probability. That's what the copula does. Now some more formal and thorough definitions and properties. Now this function C from the d-dimensional hypercube, unit hypercube into the unit interval, is a so-called d-dimensional copula or just a d-copula if C meets the following conditions. First of all, the copula is monotonically increasing in each argument. If you insert ones for all arguments but one, that is ui here, it leaves ui constant for all I starting from 1 up until d. And if you have 2 elements, A and B, from the d-dimensional unit hypercube, where each argument AI is smaller or equal than BI, and you combine it in this way, you can see that what you get is smaller it is equal to or larger than 0. And these conditions are motivated on the following side because it's difficult to interpret this. The first property must always be fulfilled by a distribution function because, well, C is a distribution. And if it were not monotonically increasing in each argument, it would not be a cumulative distribution function. So that's the same, that's actually true if it is defined as a distribution function. The second property reflects the need for uniformly distributed margins. So the marginal distributions are uniform. In German we would say gleich verteilt. The same as with a discrete dice. So 1, 2, 3, 4, 5, 6. If it's a fair dice, it should be uniformly distributed. And the third property ensures that if ui up until ud is distributed according to the copula, then the probability here of A1 being smaller than U1 and B1 and so on is actually equal or larger than 0. And the bi and multivariate margins of a copula are again copula. So if you have a d-dimensional copula, then you can take a subset of these variables, and what you get is again a copula. Now, next we need the so-called generalized inverse of a distribution G. So G is a distribution, and we need to look at the inverse, that is the quantile function. The problem, however, is that in some cases you cannot properly define the quantile function, but you need to come up with a slight trick so that you can define what we then call the generalized inverse, which is basically the quantile function. In some cases, it is not exactly equal to the quantile function. Then, with the copula and a random variable G, we get the probability integral transform and the so-called quantile transformation. What is that? The probability integral transform is if you have a random variable y and has a continuous univariate distribution function G, then if you insert y into its univariate distribution function G, you get a uniform distribution on the unit interval from 0 to 1. So if you insert the random variable itself in its own distribution function, you get a uniform random variable. And second, if you have the quantile transformation, if u is a uniform random variable on the unit interval, and you insert u in the inverse, in the generalized inverse of a distribution function G, you get the distribution function itself. Meaning what? This actually is the foundation for stochastic simulation of a random variable that is distributed according to G. Why is that? Let's assume you define a random variable G or distribution G. Now you know what G looks like as a formula, but you want to generate random numbers, random simulated observations from G. Now, on paper, you can come up with the generalized inverse of G. And what you need to do now is you need to draw random numbers from the unit interval, which is what every random number simulator does. It's actually what your calculator does. And you insert these numbers, these random numbers, u here, into the generalized inverse function, and what you get is the probability which is equal to the distribution of G itself. So what you need to do is, in stochastic simulation and Monte Carlo simulation, you need a random number generator, you need the generalized inverse of your distribution, and you need to insert those random numbers into the generalized inverse, and what you get is a random number simulator for G itself. That's the foundation of stochastic simulation. Now, next, how is this related to copulas? Let's turn to the famous Sklar's theorem. Now, Sklar's theorem, back from 1959, states the following. Let f be the joint distribution function, actually be the joint distribution function, with marginal distributions f1 and fd, then there exists a copula C such that for all x1 to xd, we have the joint distribution is given by the random univariate marginals inserted into the copula. So you need two ingredients. You need the copula itself, and if you insert the univariate margins f1, f2 up until fd, then you get the joint distribution. If the marginal distributions f1 up till fd, if they are continuous, then C, the copula, is unique. And conversely, if C is a copula and f1 and up until fd are univariate distribution functions, then f is a joint d-dimensional distribution with marginal distributions f1 until fd and a dependent structure that is captured by the copula C. And this gives you a factorization. It gives you a representation of any continuous joint distribution. The joint continuous distribution consists of two parts. C, the copula, which captures the dependent structure, and the margins F1, F2 up until Fd. And if everything is continuous, then C is unique. Now, the nice thing about Sklar's theorem is that it tells you every joint distribution includes, continuous joint distribution includes a copula. And you can try to extract this copula. And if you are modeling risks, you can use the univariate margins. You can choose a copula. You can estimate a copula from data. And what you get is the joint distribution. You can model the joint distributions in two steps: marginal behavior and dependent structure. Now, the bad thing about Sklar's theorem is that it's not constructional. It doesn't give you any idea how to choose C. It only tells you there is one C, and if the random variables are continuous, then C is unique. It doesn't tell you how to choose C. You don't know anything about C. So these are the two important statements from Sklar's theorem. First, under the assumption of the theorem, from every joint distribution, you can derive a copula C that completely captures the dependent structure between the marginals. And second, you can construct any new arbitrary high-dimensional distribution simply by combining known copulas and known marginal distributions. Next important fact is F1 and say Fd do not necessarily have to come from the same random statistical distribution family. So it could be that you say F1 is a normal distribution, F2 is a t distribution, F3 is a beta distribution. Now you can do this, and this is no problem. Sklar's theorem still holds. So both possibilities are of interest in risk management, trying to extract the copula from data, but also if you have some model and you want to apply copula in this model, you can choose the copula based on the theoretical properties of that particular copula model. So you model the dependent structure first in a multivariate data set, and on the other hand, extremely flexible high-dimensional models can be generated, which is actually very similar to mixture models, also in statistics. Now, I've given you this warning. Sklar's theorem only makes a statement about the existence of a copula function. It doesn't tell you anything about the exact mathematical form of the copula, and it doesn't really tell you how to use data to estimate C. This is what has been done next, and we'll be talking about these properties in just a bit. Now, let's have a look at some other important properties of copulas. First of all, it is important to know that copulas are invariant under strictly monotonically increasing functions. That is, for the joint distribution of a random vector with copula C and strictly monotonically increasing transformations T1 and TD, this vector T1 of x1, T1 of x1, T2 of x2 up until TD of xd, they also have the same copula C. So we thereby assume that the marginal distributions are continuous, and by Sklar's theorem we then have the uniqueness of the copula, which justifies using the expression the copula. It's not a copula, but it's the copula. Next, the copula C also has natural limits at the top and the bottom, and they are called the Fréchet-Höffding bounds. First, we have the following proposition. The copula C is bounded by the maximum of the sum of ui plus 1 minus d or 0, and is bounded above by the minimum of u1 and ud. And these two sides, the left-hand side and the right-hand sides, they are called the lower and upper Fréchet-Höffding bound. So those are the two copulas. They're copulas in themselves, and they are in a sense, the minimal and the maximal sort of dependence you can model using copulas. Now, a very simple example is the independence copula, which is simply taking the UI arguments of the function and multiplying them, and this is the product copula, which is equal to stochastic independence between the marginals. The upper Frechet-Höfting bound, so the minimum of U1 and the UD, is called the comonotonic copula, and it represents a perfect positive dependence of the margins, in the sense that the margins are almost surely strict monotonically increasing functions of each other. Now, you know, with correlation, you would say that, okay, correlation can be between -1 and 1. So it is actually between -1 and 1. And you would say, for example, for 1, the two random variables are perfectly linear functions of each other. And in this case, it is comonotonic copula. It means that you have perfect, not positive correlation, but perfect dependence, positive dependence, in the sense that the margins are almost surely strictly monotonically increasing functions of each other. And analogously, you have the counter monotonic copula, the lower Frechet-Höfting bound, which is derived, and it is only a copula for D equal to 2 dimensions. And it's perfect negative dependence, in the sense that x1 is almost surely a strict monotonically decreasing function of x2. Now, in addition to the mentioned elementary copulas, we have numerous explicit and implicitly defined copulas. For example, for the explicit ones, we have analytical expressions. For the implicit ones, we only can derive them implicitly from known joint multivariate distributions like the T distribution, the normal distribution, etc. And we'll start out with these ones. For example, the elliptical ones. The two ones that are of most importance to us and most interest to us are the Gaussian and the T-copula. So let's take a random vector y, which is d-dimensionally normally distributed with expected value vector mu and covariance matrix sigma. Then the corresponding unique copula is called the Gaussian or the normal copula. And it is implicitly defined by what? You take the inverse, the inverted normal distributions, phi1 inverted, phi d inverted. You insert it into the joint multivariate distribution. And what you get implicitly, you cannot write this down as an analytical formula. What you get is the Gaussian normal copula. Same one with the T-copula. Now, you can already see that the Gaussian copula has d times d minus 1 divided by 2 entries in its correlation matrix. So these are the parameters. However, they could be interpreted as correlations. Problem is, if you insert margins that are not normally distributed here, what you get is obviously a Gaussian copula, but if you combine a Gaussian copula with non-normal margins, the result will be a distribution that is not normal, and the parameters will not be equal to the correlations. They will be similar to the correlation and close to the correlations, but they will not be equal to the correlation matrix. Same with the T-copula. You take a d-dimensional T distribution, you invert the univariate margins, and what you get is the so-called student's T-copula or just T-copula, and it is also implicitly given with parameters P. This is a matrix of quasi-pseudo correlations, but we also have one additional parameter, nu, the degrees of freedom, just like with the T distribution. So this is a T distribution and a T copula. We have d times d minus 1 divided by 2 entries in the correlation matrix. These are the parameters, and you should regard them as pseudo correlations. It cannot be represented analytically, and we have one additional parameter, the degree of freedom nu. And in contrast to those implicitly given elliptical copulas, we also have many explicitly defined copulas. And the most famous family of those copulas is the family of Archimedean copulas. And the most famous ones are the Clayton, Frank, and Gumbel copula. And for the sake of simplicity, we only feature the bivariate case. So these are the Clayton, the Frank, and the Gumbel copula. And as you can see, you have explicit definitions here on this slide. Okay. Now I told you that copulas are nothing but d-dimensional distribution functions, very special distribution functions, but distribution functions nonetheless. So you can obviously simulate observations from bivariate copulas, and this is what is done here. The first one, remember that this is a copula, so the margins are on the unit interval. It means that you have a probability here, a probability here, and the more points you have here, the higher the probability is that these two probabilities from the margins are combined in the joint distribution. Now here you can already see this is the independence copula. Random behavior, no particular clustering. The normal distribution is elliptical, and you can see why it's called elliptical. You have an ellipsis here. The Clayton, Frank, and Gumbel copula, they are not elliptical, and you see it's slightly different. Okay, so these are some examples of copulas. This is the trivariate case, so it's three-dimensional. We can still plot this, but we need more observations because otherwise, because of the curse of dimensionality, 1,000 observations would be simply lost in this three-dimensional space. So this is the independence copula. This is the normal copula. And this is the T copula. And this is the Clayton. You can already see that you have a severe clustering at this point here. This is the Clayton copula. This is the Frank copula. And this is the Gumbel copula. So completely different dependence structure behavior between those different copulas. And what this in the end means is that if, for example, you have 3 dimensions, you have 3 dice or 3 marginal distributions, you take these these marginal probabilities, and they would be combined maybe here, and the more points you have at this point here, the higher the joint probability would be for these 3 observations. That's what the copula does. Okay, and we've seen all these. Now what we can do is, let's take 2 margins. We have normally distributed margins. We are keeping those normally distributed margins fixed, and we recombine them with different copulas. So we have plots of different joint distributions. Of different joint distributions. The marginal behavior stays the same. So the probability of, say, looking at -5, if you cut through here, this probability stays the same. Also, the probability of having a +4% return, if you only look at dat 1 in the second column here, isolated, the same. This probability stays the same. The probability now is we are looking at the joint probability of having -5% for the first asset and +4% for the second asset. And the random behavior of the marginal stays the same if we take a Gaussian copula with parameter, quasi-correlation, pseudo-correlation 70%, and if we change it to a Clayton copula with parameter theta equal to 3, you can see the distribution, the joint distribution, is completely different. Now, you could argue, but isn't the first asset and isn't the same asset, the marginal behavior changing? No. If you were to take each point down if you were to take all those points down and drop them down on the x-axis, you would get the same distribution on the x-axis. It's the same distribution if you cut through the x or the y-axis. Same thing with the y-axis. The problem now is that maybe, for example, this point here and this point here, they are now combined in this point. In the other plot, it could be that this point here is combined with this point, and this point here is, which used to be down here, it now switches to this combination. The same marginal behavior, completely different joint distribution. And this can easily be done in R using very simple code and working with different copulas. You can also do the same with the Gaussian copula here. You only have to switch the correlation from 70% to say -70% or to 0. And what you get is a completely different behavior. Same marginal distribution again, now with a Gumbel copula. You can see the joint distribution is completely different. And this is dependence only. This is only concerned and related to the dependent structure. Okay. What we've done now is what we call a meta distribution. What is done here is you choose any marginal distribution and you combine these marginal distributions with any given copula, and what you can come up with is a new joint distribution which has no name. So here in this case we had two different normal distributions. We combined them with a Gumbel copula, and I could now call it, this is the Weiss distribution. This is a new QRM distribution. This is the Leipzig distribution. You can see unlimited possibilities of coming up with new meta distributions, and this is why we call them meta distributions. And it's one flexible way in a bottom-up approach of modeling risk factors. You have a set of univariate distributions for your risk factors, and you choose individually, univariate distributions we've seen before, like a beta distribution, like a normal distribution, like an inverse Gaussian distribution. And you combine those different distributions with any given copula, and what you come up with is a multivariate meta distribution with these univariate marginals and this particular copula function. Now, due to the fact that the marginal distributions do not have to be identically distributed, each risk factor can be modeled individually using a different univariate marginal distribution. Therefore, one does not have to make distribution assumptions that are more or less correct for all risk factors. You do not need to have to choose the normal distribution for all risk factors, but you can choose individual distributions for each and one risk factor. And the copula is a good possibility to capture the complete dependence structure between two or more random variables. However, there exists a variety of measures for different aspects of dependence, so you need to be careful when selecting the copula and need to make sure that you measure risk in a proper way. So let's talk about some measures how you can describe dependence based on copula functions. And the first one is linear correlation. You all know about linear correlation. We have a correlation factor rho between x1 and x2, and it's a measure for the linear dependence between the variables. And without proofs, you can easily show some very simple properties. For example, the first one is if you have a correlation of 1 or -1, x1 and x2 are perfectly linear dependent. That is, you have x2 being a linear function in x1 or the other way around with any parameter alpha and beta unequal to 0. Very simple result, which is already in the name. Linear correlation, perfect linear correlation means x1 is a linear or x2 is a linear function in x1. Now, linear transformation. Correlation is invariant under monotonically, strictly monotonically increasing linear transformations. That is, if you have x1 and x2, and you transform x1 and x2 linearly by taking alpha 1 plus beta 1 times x1 and alpha 2 plus beta 2 times x2, the correlation of this linear transformation is the same as the original one. Meaning that you can take two random variables, and if you look at linear functions in x1 and x2, the correlation stays the same, but you cannot drop this assumption of a linear transformation. This is why the copula measures more dependence in a way than linear correlation, because we've seen with the copula functions, it's very simple that it is, where is it now? Here, the copulas are invariant under strictly monotonically increasing transformations with no mentioning of a linear transformation. For any transformation, copula is invariant. For linear correlation, we have to insert increasing linear transformation. That's the difference. Let's go back to our properties. Next thing, the correlation is defined for random variables with finite variances only. In our applications, this is usually not a problem, but statistically, you have to keep in mind that it is only defined for random variables with finite variances. Now, fallacy 1. You could think that the marginal distributions and the pairwise correlations completely define the joint distribution. False. Why? Simply construct a bivariate standard normal distribution and a mixture of the Frechet-Höfting bounds with two univariate standard normal distributions as marginal distributions. You get the same correlation, completely different joint distributions. So you cannot construct the same joint distribution by only knowing the correlation. It's not sufficient. The second fallacy, for two marginal distributions f1 and f2 and a correlation between -1 and 1, a joint distribution f with marginal distributions functions f1 and x2 and correlations rho can always be specified. No. The problem is that we need to look at the so-called attainable correlations. If you fix the marginal distributions, it could be that the only correlations you can attain is a strict subset of the interval between -1 and 1. It could be that if you fix f1 and f2, you can only get a correlation of, say, -70% up until, say, 90%. Could be the case. Yeah? So that's why only attainable correlations are possible, and this pretty much depends on the distribution functions, on the marginal distributions. Okay, so false. It's not sufficient only to fix the marginal distributions and the correlation. So what else can we see with the copulas? Basically, rank correlations. Rank correlations are measures of dependence that depend only on the copula and not on the marginal distributions. What these two fallacies tell you is correlations depend not only on the copula, correlations also depend on the marginal distributions, and this is what we want to prevent. So next, we look at rank correlations. These are measures of dependence that do not depend on the marginal distributions, but only on the copulas. So as the name suggests, we are looking at ranks. So let's take some observed values. We have 1, 2, 3, 4, 5. Those are our indices. We have 3, 6, 1, 0, 8 as the observations. And if we take the ranks, obviously 0 is the smallest number, so it gets the rank of 1. 8 is the largest value, so it gets the rank 5. And we have 1, 2, 3, 3. 6 is the fourth largest, the second largest and the fourth smallest number. And 5 is the largest, so these are the ranks. 3, 4, 2, 1, 5. Then we can define Candel's tau, which is a rank correlation coefficient, which is defined as what? It's the expected value of the sine of x1 minus x1 tilde times x2 minus x2 tilde, where x1 tilde and x2 tilde denotes an independent copy of x1 and x2. And this is basically what it's more or less, it's a correlation of the ranks. Slightly different with Spearman's row, it's also a rank correlation that is defined as the correlation, the linear correlation between the variables after applying the probability integral transformation, which we've already seen. So inserting f1 and x2 in the distributions of x1 and x2, that's Spearman's row. So both rank correlation coefficients are symmetric. They have the value 0 for stochastically independent variables, and they take on the value 1 and minus 1, now not for linear, perfect linear correlation, but for comonotonic and counter-monotonic variables. And we've already seen with the Frechet-Hefting bounds that counter-monotonicity and co-monotonicity, this is actually what we are looking at when we are looking for measures of the complete dependent structure. And in addition, it is very important to see that Kendall's tau and Spearman's row, they are actually functions in what? In the copula C. So if you know the copula, you can already calculate via this double integral Spearman's row and Kendall's tau. So they are functions in the copula of the joint distribution, and they are functions in the copula only. No need to know the marginals. This is one difference to linear correlation. False conclusion 1, the fallacy 1, remains valid for rank correlations too. So margins and rank correlation do not unambiguously determine a distribution. Simple example, we take the same marginal distributions, two different Archimedean copulas with the same Kendall's tau. We get two different joint distributions, but the same Kendall's tau. So it is not sufficient to just know Kendall's tau. But fallacy 2 is resolved. That is, for arbitrary marginal distributions, a joint distribution with a given rank correlation can always be constructed. So if you only know the margins and you know the rank correlation, this is true that you can always construct a joint distribution with these margins and this particular rank correlation between 0 and 1. Some examples. Gaussian copula with a parameter rho. You get Kendall's tau and Spearman's row by these formulas. It's even simpler for Clayton and Gumbel copula. It's actually theta divided by theta plus 2, or 1 minus 1 over theta, though this is Kendall's tau for the Clayton and Gumbel copula. And then, last but not least, we get to the concept of tail dependence, which attempts to measure the dependence of the random variables in the extreme tails of the distribution. And generally speaking, we want to measure the conditional probability that one tail will exceed a certain threshold given the other edge has also exceeded. So this means the first asset crashes. What is the conditional probability that if we have a crash in asset 1, we also have a crash in asset 2? So if BMW stock crashes, what is the probability, the conditional probability that if BMW crashes, Daimler stock crashes as well? More formally, we define the coefficient of lower tail dependence for a random vector x1 and x2 by the following formula. It's the limit of q, which is a quantile, going to 0 of the probability that x1 is smaller or equal to a generalized inverse, so basically a generalized quantile, if x1 is also below or equal than the generalized inverse of x1. Given, of course, that this limit exists. And for f1 and f2 being continuous, we have that the coefficient of lower tail dependence is the limit of the copula at QQ divided by Q. So we go to the left tail, we go to a very, very small probability, and we are looking at the limiting behavior of the copula, and we get a coefficient that is between 0 and 1. And if it's 0, it's tail independent. So the tails are not depending on each other. And if it's 1, we have a very strong dependence, meaning that a crash in x1 forces a crash in x2. Same on the right-hand tail. So we also have a coefficient of upper tail dependence, which is defined very similarly. And now we need to look at the survival copula C hat, which is simply given by 1 minus u minus v plus the copula of 1 minus u and 1 minus v. For those of you who are interested more in, let's say, insurance mathematics, you might have heard something like this. G defined as 1 minus f. Any idea how this is called in insurance mathematics and in statistics in general? How is this called? This new distribution G. How is it called? This is the so-called survival function. We have this in statistics in general, but especially in insurance mathematics, because if F is the distribution of a person dying in life insurance, then 1 minus F is the probability of survival. And as you can imagine, in health and life insurance, you're very much interested in the probability that a contract, a claim, a policyholder ages up until age 80 or 85, or if he survives until age 90. So you're more interested in survival functions, and this is how they are defined in statistics. And the survival copula then obviously is the copula of the survival function, not of f, but of 1 minus f. And these are the tail dependence coefficients of some parametric copulas. For the Gaussian copula, lambda L and lambda U are 0. The Gaussian copula is so-called tail independent, tail independent, yes. The T copula has the same coefficient of upper tail dependence as for lower tail dependence, so we call this symmetrically tail dependent. And the Clayton copula has a lower tail dependence and the upper tail dependence 0, so we call this a lower tail dependent copula. And the Clayton copula, because it is lower tail dependent, it can model the joint distribution and the joint probability of a joint crash, and this probability is higher than the probability of a joint boom. Ergo, the Clayton copula is frequently used in financial applications because we can model crash risk and tail risk with the Clayton copula, and it does not put too much emphasis on a joint boom. That's the Clayton copula. And with the Gumbel copula is upper tail dependent. Okay. Densities, distribution functions, and sampling from copulas. As you've seen, a copula C is already a distribution function. And for a copula C, there also exists a copula density. Therefore, we can also exploit maximum likelihood as a principle to estimate the parameters of C. We can also generate random numbers via Monte Carlo simulation, and you've already seen this because those plots of the copulas I've shown you, those were based on, not these ones, but these ones, those were based on Monte Carlo simulation from a given Clayton copula, from a Clayton copula with certain parameters. So you can do maximum likelihood. You can do simulation, as I've done here. And you can use more computational effort, and you need more computational effort to simulate from those high dimensional copulas, because obviously it is done in multi-dimensions. Okay. Finally, you can, just as with any mixed distribution, you can also come up with what we call mixture distributions and mixture copulas. Now, in statistics, you can easily show that if you do a convex combination, and this is a convex combination, it's the sum of weighted distributions Cj. When the weights are all non-negative and add up to 1, we have a convex combination. And a convex combination of any distribution is called a mixture distribution. And it is, again, a distribution function. And the same goes for copulas. If you mix copulas via a convex combination, you get a new copula, and we call these mixture copulas. One advantage is that you can combine many different tail behavior copulas of different parametric copulas. The disadvantage is that it is numerically unstable and you have a rapidly increasing number of parameters, and this is done in high dimensions, so you need even more data to estimate these mixture copulas. Other flexible copula models. I don't want to go into too much detail here. The most famous ones are so-called nested Archimedean copulas and so-called pair copular constructions or Wien copulas. If you do some modeling with these, you have to go to the literature and look these models up. Wien copulas or PCCs are probably very famous ones here. And what you try to do is, even in high dimensions, you want some flexibility when it comes to the parametric family from which you take the copulas. So if you don't want to take a Gaussian copula, you don't want to take a student copula, but you want to recombine those different copulas so you have more flexibility when it comes to the modeling of your dependent structure. Yeah, and in case of Wien copulas, you have different parametric copulas that are nested within each other in order to generate high dimensional building blocks and high dimensional copula models. Again, look in the literature, look to the literature. It also builds on combinatorics and discrete mathematics. It's way too complicated to present it here, but this is one area of research where I've been very active over the last 10, 15 years, and you can have a look at the most recent research literature on copula modeling. How do you estimate the parameters of a copula? It's basically done by maximum likelihood. The problem is that you have to estimate the parameters of the marginals and the parameters of the copula, and you can do this in different ways. One way is to estimate all parameters in one step. The second way is to estimate first the parameters of the marginals and then the parameters of the copula. And the third way is basically to use the empirical distribution functions for the marginals and then insert those empirical distribution functions in the model and only estimate the parameters of the copula. So the first is full maximum likelihood. Estimate all parameters of the entire distribution in one step using ML. Very slow, very numerically sensitive to local maxima, and it is often distorted by incorrect distributional assumptions, because if you miss or if you make a wrong assumption on the marginals, well, the results will be horrible. The second one is called inference for margins. What you do is you first estimate your marginal distributions, you plug in the parameters in the likelihood density of the copula, and then only estimate the parameter copula parameters in the second step. It's faster, but it still depends on the distributional assumptions for the margins, and the best way to estimate the parameters, I guess, is what we call pseudo maximum likelihood or canonical maximum likelihood. You replace the margins with the corresponding empirical distribution functions, which is basically using so-called pseudo-observation values based on a rank transformation of the original data. And then you insert these values in the copula density and you do regular maximum likelihood. It does not depend on the distributional functions for the margins. It's quick and it's probably the best way of estimating the parameters of your copula. Finally, you can also do minimum distance estimation, which is completely different. You look at an error function. You look at an estimation error between your copula model and your data set, and then you estimate the parameters by minimizing this error function, usually quite small, semi-parametric in nature, also uses pseudo observations, probably not your best choice, it could be in higher dimensions. Okay. And also, last but not least, we have the method of moments, which is you take, for example, Kendall's tau, you take Spearman's rho, and you estimate the copula parameters by matching the Kendall's tau of your model to the one that you can estimate from your data. Very simple, very fast, but it can only be done for single parameter copulas. So that's a disadvantage. Okay. Now I still have a little bit of time, so let's look at a practical example. We've learned a lot about the theory of copulas, so let's do this in practice. We will apply the theory to a return series of 2 large US stocks and model the joint behavior in R. We download the stock data from Yahoo Finance. We calculate pseudo observations from the log returns. We determine a suitable copula model, and then we fit the copula model to the pseudo observations, model the marginal distributions, and we simulate new observations from the fiddle models. So we download the data. We get price 1, price 2. Those are the price data. We calculate in lines 10 and 11 the return data as the log returns. Very simple. We then plot the data, Microsoft against Morgan Stanley. We can see already could be that the dependent structure is elliptical, but that's not so sure. We then estimate the correlation, Pearson correlation, Kendall correlation, Spearman's rho. So we have 51% Pearson, Spearman-Pearson correlation. Kendall's tau is 30%, Spearman's rho is 43%. We measure the tail dependence. We can do actually this. So we fit lambda. This is a function in R. You can see that actually the lower tail dependence is 42% and the upper tail dependence is 25%. So what do we see? Tail dependence? Yes. Symmetric tail dependence? No. Lower tail dependence is higher than upper tail dependence. So any symmetric tail dependent copula is ruled out. Now, what we can do is we can use the Vine copula R package. It offers the function by copula select to perform copula selection based on base information criterion or archaicus information criterion. The estimates are obtained by maximum likelihood, and the parameter family set for this bicop select function, it allows for specifying a subset of copula families. We can start by Gaussian T, Gumbel, Clayton, Frank copula, and let R select the best fitting copula. So we'll do this. We'll start with the library. It's all in the library Vine copula. We estimate the pseudo observations, which is done by the function pops, pseudo ops for return 1 and return 2. We select a suitable copula model. So we allow the independence Gaussian, Student T, Clayton, Gumbel, Frank, and Joe copula. And we say copula model by cop select U and V. Those are the 2 vectors of pseudo observations. And family set is equal to 0 to 6. Now we get the summary, and the parameter is 47 for the first parameter and 4.83. The family that is chosen is the student T copula. So we have 2 parameters. Kendall's tau is 31. The empirical Kendall's tau is 31. So we're pretty good when it comes to Kendall's tau. Upper tail dependence is 20%. Lower tail dependence is 20%. So we are quite okay with the upper tail dependence, but lower tail dependence not so much. Why is this done? Well, probably because these other copulas are even worse. They are not better suited to model the data than the student T copula. And we have some statistics, the log likelihood and archaicus information criterion. Then we initialize T-cop as a T copula, and we simulate pseudo observations based we define the pseudo observation matrix, and we combine pops and pops return 2. And then we fit a model, we fit the copula based on the T copula, based on the observations, the pseudo observations using maximum likelihood. And what we get is rho and the degrees of freedom, and we can plot the perspective here of this copula, and you can see it looks like this. Okay. Now we can sample pseudo observations from the estimated key copula. However, the pseudo observations have the same correlation as the original returns. Now the T copula is particularly well suited for modeling extreme events, And as the T-copula is symmetric, it is not suited to capture asymmetries in the data. However, we are neglecting this now in this example. And before pseudo observations can be compared to the actual returns, they have to be retransformed based on the marginals. And this is done now on the following slides. We do the following. First of all, we need, and sim is the length of return. We simulate the number of pseudo observations equal to the length of this vector. We simulate via R copula, random copula, and sim these number of observations from the T copula with 2 dimensions and the parameters equal to rho and df. And then we plot those pseudo observations from the copula. Again, this is the copula, not the joint distribution. So it looks like this. And then we model the marginals based on a student T distribution. This is sufficient in our setting. We are modeling the joint distribution. We could have used better and more sophisticated model, but let's assume we are taking a student T. So we are using a scaled T quantile and a student T distribution. So fit 1, fit 2, we fit a T distribution based on return 1 and return 2. We simulate quantiles from these fitted T-distributed marginals, and we insert the pseudo observations from the copula. Again, remember the quantile transformation. We are taking the pseudo observations from the copula, we are inserting it in the quantile functions of our marginals, and what we get is the joint distribution. And this is the result. We are plotting the return and return 1 in black, and our simulated returns from our model are shown in red. So basically we would say, we will never, because this is simulated data, these are simulated data, we will never obviously match each point because it's random. But the general structure of the data looks the same. So we would argue, well, this could be a very suitable model for modeling the joint behavior of the Morgan Stanley and the Microsoft stock. Okay. So this is a very short introduction to copulas. Do you have any questions? Quite a lot of information to process. Someone is writing in the chat window, so let's wait for that. Any question? Again, please at home try to try out the R code yourself. If you find any problems or if you have found any errors, please tell us, and then we can correct the R code. But it should be working. Do you have a literature recommendation specifically to practice R and deepen the understanding of R? In R in general, there are too many books on R. You can also download PDFs and scripts from the internet that give you an introduction to R. If you are more interested in the practical applications, you should use the book by Jon Danielsson, Financial Risk Forecasting, which is on one of the first slides in the literature. And the references. Any other question? We have downloaded the stock data from the internet, right? Yes, exactly. If you use the same R code, you should be able to download the data, and then you can try out the R code. Last week, the available quotes, that's actually very detailed. Let's talk about that later on. Yeah. Any other questions concerning our copulas in general? If not, then thank you very much for your attention and see you next week. And I will now stop the recording.